Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and today I'm going to talk with you about the fourth reason why the mainstream definition of calculus is flawed. So let's begin. Now, you'll notice that in the previous version, in the previous three videos, and let's just summarize, we had three reasons. These are the three reasons, the first three here, okay? And the most important first problematic reason is that the limit L is used in its own definition. So something that is used in its own definition is uh, is not a good thing because it produces a circular definition. So it's problematic. I mean, if you say x consists of x plus 2, you still don't know what x is. Okay, you haven't actually defined x. So, and a lot of mainstream academics love to say define x and then just do whatever they please according to their whimsical notions. That's just nonsense. The second reason is that there is no such thing as a real number. So, um, a number, by definition, is a name that is given to a measure that describes a ratio of magnitudes. Okay, so there's no such thing as an infinitesimal expansion where you have 1.414 dot 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 or 3.14159 dot dot dot. Those are not measures. Those, in fact, are just simply rational numbers followed by an ellipsis. Okay, nothing goes on forever, and this measure, either of these measures, can never be complete. Certainly not in the sense of algebra. Okay, not in the sense of algebra. In geometry, yes, but not in algebra, because algebra transitions from geometry through the abstract unit. In other words, algebra uses a unit whose type and size is irrelevant. It doesn't care about the size or the type of unit, whereas geometry does. Okay, and one of the problems that comes up immediately when you begin to think about these things is that if you, for example, have, let's say, a right angled triangle, isosceles like that, and you realize this notion or this idea of square root 2 when you try to measure this side using this side. But the same thing happens with a bigger isosceles triangle. You still realize square root 2 when you try to measure this side using this side. Okay, in other words, the measure is the same as division. So you say, okay, this side goes in once, and then when you break it down into tenths, you see it goes 4 times. You break it down into hundredths, it goes 1/100th, and so on. Okay, so there is actually no number square root 2. Square root 2 is just a symbol for a constant. Okay, as many places as you can measure it, but that constant is not square root 2. And the same thing happens with a circle. Okay, any circle that you use, because the symbol pi is realized from the failed measure of the circle's diameter, of a circle's diameter to its circumference. If you try to measure the circumference of any circle, it's 1, 2, 3, and a little bit left over. Okay, so pi is also just a constant. So there's no such thing as a real number or an infinite decimal expansion. And what's even really more laughable, very laughable in fact, is when idiotic mainstream mathematics professors and teachers write a third is equal to 0.333 dot dot dot. Now, if theoretically this could stretch to infinity, don't ask me how that could happen. This would break the theorem that says you can only represent a number in a given radix system if its prime factors are contained in the base. Okay, so 3 is not a prime factor of 10. And there, in one of my famous articles, I proved this in very few pages, about 4 or 5 pages. It's a theorem that no mainstream mathematics academic knows because they've never understood or even cared about the definition of number. They call anything they like number because they're idiots. Okay, so therefore a third is not equal to 0.333 because a third has no measure in base 10. Okay, now today I'm going to deal with the fourth reason, which is simply this, that the limit L is never contained in the sequence of finite differences. And more importantly, that there is no form or method whereby the rise over run of a tangent line slope can be expressed in terms of a non-parallel secant line. What does that mean? That means that if you have a curve like this and a tangent line like that, it doesn't matter how many secant lines you use. There is no secant line finite difference. So for example, if you look over here, you might say, okay, this is the first secant line slope. Okay, this is the first secant line slope. First one, second one, third one, and so on. Okay, but there is no rise over run unless you're using the new calculus, of course, in which case there is. And the reason for that is that in the new calculus, you're using a parallel secant line, not a non-parallel secant line. So in the new calculus, any parallel secant line will represent the same slope as a derivative. And that's why the new the new calculus is 100% rigorous. And your bullshit mainstream calculus is just a pile of crap, which has always been. Now, there's something I wanted to also go back to that I mentioned yesterday, and it's this statement by Cauchy. So if we look at what Cauchy said, he said that, let's go back there. Yeah, he said that a function needs to be continuous, but the problem is if that function has kinks, like you see over here, the finite difference will not necessarily represent a non-parallel secant line. So you'd have a problem. In other words, what I'm saying is Cauchy didn't notice that continuity was not sufficient. Just like the moronic admins of Wikipedia who think that you can use the mean value theorem and the fundamental theorem without F being smooth. So if you look at the fundamental theorem entry, it says that it only need be continuous. And then, of course, you get some very stupid Greek academics who think that the mean value theorem only works in one dimension. And it's kind of insane because if you have a parametric function or a vector function or anything like that, and you follow the same rule that you normally do with one-dimensional calculus, you're using the mean value theorem, you idiot. Do you understand that? I mean, you can't say, okay, here I have a parametric equation of 3t squared t and 1 over t like that. And then you differentiate that and you say that's 6t, that's 1, and that's minus 1 over t squared. You can't do this, you morons, if the mean value theorem doesn't apply. Do you understand that? So this Greek academic from Athens, a bumbling idiot who was trained in Western universities, doesn't get that. Okay, he thinks that the mean value theorem doesn't apply in higher dimensions. Take it from me, people. If you do not have a smooth curve in calculus, all the methods of calculus are null and void. You can't use them. They're just garbage. You can toss them out of the window. And the reason you can toss them out of the window is this, because in your calculus, your bullshit calculus, you're, and it is bullshit for a very good reason. Now, how come I can't make that thick? Let's make it thick. Okay, so this black function like that, okay, it's a black function, okay. Should have done that. This black function here, 1, 2, 3, 4, right? If you took a finite difference between these 2 points, you're doing something really stupid because there's no non-parallel secant line, There's no parallel secant line. There's no secant line there, you incredibly stupid morons. Do you understand that? So Cauchy was wrong. You cannot just take a continuous function. You need a smooth function. Okay, Cauchy did not understand calculus, just like all your mainstream professors, without any exception of mathematics, and your mainstream teachers do not understand calculus or the reasons it works. And coming back to my main topic of today, like I said, even if you have a rise over run that is a rational number, okay, so even if, let's say, the slope is 3/4, this particular method here will never result in 3/4, okay? Never, because a non-parallel secant line will never give you 3/4. And you may say, well, that's not a problem. We're looking at the limit as the sequence converges. Well, there are problems because there's no such thing as a real number, and the method you're using makes an assumption that the curve is smooth, and then you have later on idiotic theorems like proving whether the point is differentiable, and confusing because you go back and forth with continuity and smoothness, and your whole mainstream calculus is a spaghetti of bullshit. It's a spaghetti of circularity. Your professors are horribly confused. Okay, they've never understood calculus. They've never understood mathematics, never mind calculus. So if you ask any one of your moronic professors what is a number, they can't tell you. Okay, so this is pretty much it. This is the fourth point, and there are 2 points left that I'm going to cover in my article, and I'll just name them briefly. And the fifth one is, in order for this verification, because remember, mainstream guesses and then tries to verify, it must be possible to have a hole at the point of tangency. That's very important for them. So they have what's called holy theory. And then there's a sixth reason, which is that, let's get there. Oh, well, I didn't put down the sixth reason, did I? Actually, the sixth reason is that they don't understand the limit definition which they use. So I will actually fix up my article. Here it is. The sixth reason is that because they don't understand the limit definition, they fail to realize that this, which is an identity from my historic geometric theorem, actually exposes a fatal flaw. This here, all these values here are constants. They do not change. Okay, so for a given non-parallel secant line, for any given non-parallel secant line, let's just come back over here and clean this out. Don't save, and let's just get a new paintbrush. Okay, so for any, there's a tangent line. For any non-parallel secant line, this expression here equals to f prime of x plus q of xh. This is my historic geometric identity. This here means the slope of the secant line, okay? The slope of the non-parallel secant line. This here means the slope of the tangent line. And q of xh is just the difference in slopes between these tangent lines, okay? Between the tangent line and the secant lines. That's all it is. They're all constants. So for example, if you had to say, take the limit of this last term as h goes to 0, the left side would never equal to the right side unless, of course, f is straight, in which case this here does represent rise over run. Do you see how simple that is? And of course, the bullshit artists of mainstream academia, such as Zelos Malin, Jean-Pierre Massager, Professor Gilbert Strang, Professor Jack Azinger, all those incredibly stupid morons, will tell you that that I'm basically not talking the same language as they are, but in fact, I'm correcting them and showing them the error of their ways and their foolishness. Okay, so you cannot have this thing here going to 0, because then the fundamental identity falls apart. And this, by the way, has nothing to do with that garbage entry on Wikipedia called the fundamental excrement lemma. Actually, it's called fundamental increment lemma, but it's excrement because it deals with a bullshit concept called an infinitesimal. There is no such thing as an infinitesimal. And do you know who invented that concept? Who put that concept on the map? It was some incredibly foolish Jewish mathematician called Abraham Robinson. His whole work is a mountain of crap, and so is non-standard analysis. It's absolute rubbish in every single respect you can think of. Okay, so if you're not already a subscriber to my channel, become a subscriber. Okay, so I've gained a lot of members, and I'd like you to join my members only channel. Okay, so if you go to any of the videos like this, and you click on the join button, all right, let's go there, click on this join button. For only €4.99 a month, you can get access to a lot more. You can get access to this incredible directory here, which is for members only. And I place a lot of goodies in this directory here. I place a lot of goodies in there. I'm also currently working on some research which is intended to straighten out once and for all the concept of number and how we go from geometry to algebra, and more importantly, how we learn the right way and how it affects us, not just for a little while in our lives, but how it affects us throughout our career and our lives if we learn the wrong way. In other words, once you start learning incorrectly, it carries over into every one of your future ideas. In other words, you're basically piling shit on top of shit. And at the end of your life, you really just have one big shit pile, which means an old professor of mathematics or calculus. Okay? So become a subscriber, click like, follow me on academia.edu, and I'll be chatting to you soon about reasons 5 and 6. My name is John Gabriel. This is New Calculus Channel. Till next time.